Welcome back to Applied Mathematics. In this video, we're going to be simplifying radical expressions. The idea here should be familiar to you. It's really nothing new, as has kind of been the theme for the last several lessons. The big idea is realizing that what you already know still applies. You are very familiar with the process of combining like terms. If you have like variables, 3x plus 2x, you can add the coefficients together and get 5x. If you have unlike variables, 3x plus 2y, there's nothing else you can do and you're kind of at a loss. You can use other things instead of variables. We've done that quite frequently using like units, right? 3 feet plus 2 feet is 5 feet. But then if you have something like 3 feet plus 2 inches, well, those are not like units, but here we have a little bit of flexibility because 3 feet is the same thing as 36 inches. So suddenly we're able to make things work. Although, not always, right? 3 feet plus 2 ounces, well, feet is a measure of length, ounces is a measure of weight. In fact, we can go so far as to say that that's nonsense. Trying to add a length and a weight doesn't make any sense. It doesn't matter that it's as simplified as can be. Having written it in the first place means that something went very wrong for you earlier on. Now, I want to do the same thing with radicals. Let's try that one more time. Now it looks like a 5. 3 times the square root of 5 plus 2 times the square root of 5. Well, these have a common factor of square root of 5. Something times square root of 5 plus something else times square root of 5. They are like, we can combine them by adding the coefficients, and we get 5 times the square root of 5. This can become a little bit tricky because sometimes the radical is hiding from us. Right? Something like 4 times the square root of 6 plus the square root of 24. Well, we've seen in a previous video, the square root of 24, we can rewrite that as the square root of 4 times the square root of 6. What am I doing here? Right, so the square root of 24 reduces and can be rewritten as 2 times the square root of 6. And now we have 4 root 6 plus 2 root 6, which all told is 6 root 6. I don't know why I have such a fascination in these examples with repeating numbers. That is entirely just numbers coming off the top of my head, and that's where they end up. The same thing can still work out if you have more involved expressions. Right? If I have x times the square root of 75x plus 4 times the square root of 3x cubed. Well, 75x is a radical that reduces. I can rewrite 75 as 25 times 3, and 25 is a perfect square. So that first radical reduces and can be rewritten as 5x times the square root of 3x. The second radical, I have x cubed, which I can split up as x squared times 3x, and the square root of x squared is just x. I've said it every time it comes up, but I'm not going to stop now. If x could possibly be a negative number, bad things might have happened in that step. I am assuming that my variable is a positive number, so I can sidestep all of the trouble, all of the arguments. That's something I can do for right now. Moving onward, it might not be something you can do in a future course, so it's something you always have to be careful about. But now that I have done this, I recognize that both of these have a factor of x times the square root of 3x, and then just a constant coefficient in front. So these are now like terms. And because they are like terms, I can combine them by adding the coefficients. That's it. That's all there is to it. A little bit trickier sometimes is when we start introducing some multiplication. And I'm going to jump us right in off of the deep end. If I have the square root of 6 times the square root of 2 plus the square root of 3. Well, all of the rules of algebra still work. This is something multiplied by stuff in parentheses. I can use the distributive property to rewrite this as square root of 6 times square root of 2 plus square root of 6 times square root of 3. Now I can kind of work backwards of what I had been doing. Square root of 6 times square root of 2 is the same thing as the square root of 12, and square root of 6 times square root of 3 is the same thing as the square root of 18. Having done that, maybe I can reduce from here. 12 is 4 times 3, and 4 is a perfect square. 18 is 9 times 2, and 9 is a perfect square. So I end up with 2 square root of 3 plus 3 square root of 2. At this point, unfortunately, there's nothing else I can do. Square root of 3 and square root of 2 are both reduced as far as possible, and they are not like. So we're kind of stuck. And that's just something that can happen, the same way that when you're working with variable expressions, right? If you end up with 3x plus 5y, there's nothing else you can do. If you end up with something times the square root of 3 plus something times the square root of 2, there's nothing else you can do from here. Right, before I move on, I do want to again address the idea of calculators. Apparently my calculator camera isn't working right now. Sorry about that. But you can enter this expression, square root of 6 times square root of 2 plus square root of 3, into some calculators, and they will spit out 2 root 3 plus 3 root 2. It's, again, not a given. It's not an every calculator can do this, but there are some that can. It can be very finicky. I don't want to show you specific details on my calculator because every calculator does things very differently for trying to enter an expression like this. But play around with it if your calculator has been pretty good with pretty print in the past, and you might get something worthwhile out of it. But as with everything else we have done, sure, we can do this working with numbers, but working with variables is probably where things are going to show up most often. So just a very similar example. Let's go to the square root of 5x times the square root of 10 minus the square root of x. Yeah, just something simple like that. Again, we can use the distributive property. And I'm going to skip a couple of steps at this point because you know what's happening. We're going to multiply the square root of 5x times the square root of 10, and we're going to get the square root of 50x. we're going to multiply the square root of 5x times the square root of x, and we're going to get the square root of 5x squared. From here, we're going to notice on 50x, well, 50 is 25 times 2, so 50x is 25 times 2x. And then, of course, 5x squared is x squared times 5. So with variables, we can use the exact same process. We can get the exact same sort of a result. And that's something that's worth knowing and worth being able to do, because this is definitely not something that a calculator can help you with. Things can get a little bit more complicated. 2 plus the square root of 6 times 3 minus the square root of 2. Here we are multiplying two binomials together. So use the distributive property all over the place. 2 times 3 is 6. 2 times root 2, root 6 times 3. Root 6 times root 2. The one radical that reduces. We've seen exactly square root of 12 before. It reduces to 2 square root of 3, same as it did before. Now that we know that that's what happens, we don't have to write it out twice. And then we have 4 terms. None of them are like. We have square root of 2, we have square root of 6, we have square root of 3. They're all different. Nothing else we can do. That's the end of the story. The last thing that I want to talk about is the vocabulary of a conjugate pair. You have seen this vocabulary before. I've mentioned it before in this course. A conjugate pair is two numbers that are being added, and then the same two numbers being subtracted. The reason that a conjugate pair was useful previously is because it is the factored form of the difference of two perfect squares. We can use that to our advantage. Whenever we have the difference of two perfect squares, whether a or b itself had a radical in it, well, once you square it, the radical is going to be gone. So if I have something like square root of 2 plus square root of 3, and I multiply that by its conjugate, which is square root of 2 minus square root of 3, well, you can remember the formula if you'd like to. Sometimes that is useful, sometimes it's not so much. You can multiply it out longhand, it will always work. Root 2 times root 2 is the square root of 4. Root 2 times minus root 3 is minus root 6. Root 3 times root 2 is plus root 6. And then root 3 times minus root 3 is minus root 9. The square root of 4 is 2. Then we've got minus root 6 and plus root 6 that are going to cancel each other out. And then we've got root 9, which is 3. 2 minus 3 is negative 1. For now, just recognizing, sorry about that. For now, just recognizing that this is a thing, this can happen, is all the more I'm looking for. As we move onward, we'll start playing around with this a little bit more. There are a couple of things that we can do, very powerful techniques in mathematics, that rely on recognizing that multiplying by a conjugate is going to simplify and get rid of a radical. Again, for right now, just being able to do the multiplication is good enough. I think that's enough. There's a lot in here. We went through it quickly because technically speaking, it's nothing new for the most part. But it's applying things that you already know in places that you don't necessarily expect it. So take some time, digest it, make sure everything makes sense to you, and I'll see you in the next video.